The Big Bang did not bang. It did not explode. It was not a bomb. It was not a detonation or a conflagration. There was no blast, no debris, no shrapnel. The universe was simply smaller in the past, and it will be bigger in the future. And that is not the only misconception you may have about the Big Bang. To begin with, the Big Bang didn't happen anywhere. It happened everywhere. It was not an event in space, but rather an event in time. It was the tick on a clock, not the notch in a ruler. It occurred in the finite past of everything in the cosmos. Every atom, every particle, every point can trace its evolutionary origins back through the eons to the Big Bang. The Big Bang happened in the room you're in right now. It happened in the Andromeda Galaxy. It happened inside you. It happened within the entire expanse of the known and unknown universe. The entire universe was smaller, hotter, and denser in the past. Now it's not. That is the great lesson of the Big Bang. And so the universe has no center and no edge. It expands from nowhere and expands to nowhere. The universe did not originate from a single point in space. The Big Bang was a point from which space originated. Yet in these statements lies an inconsistency, a paradox. 13.787 billion years ago, our theories tell us that the universe, the entire universe, regardless of its size, even if infinite, was contained somehow in a singularity, a point of infinite density and no spatial extent. But this makes no sense. This does not obey the rules of reason or logic. And this is because the Big Bang singularity is not a true representation of what everything was. It is simply a heavy hint that our equations, our maths, our physics is dysfunctional. The singularity is a sign that we do not understand our origins, the earliest moments of the Big Bang. But in the darkness of that uncertainty is nurtured the seed of a new awakening. For in our ignorance of the Big Bang, we have the opportunity, for now only seen as the ghosts and whispers of mercilessly complicated mathematics, to pierce the veil of our own beginning, to try and deduce what came before the birth of everything. Because at one time, there was no universe, and then there was. This is the mystery of creation, the paradox of our reality revealed by the existence of the expansion of the universe. But was that beginning truly the beginning? Did time start with the Big Bang? Did our universe come into existence only at that moment? Or was there something before, either similar to our cosmos or entirely different? If the Big Bang was the beginning of everything that we know, was it also the beginning of literally everything? Or is our universe just a small part of a grander fabric, a greater story that has been told since the distant ages of time past and will continue to exist well after our cosmos has sunk into cold oblivion? In 2022, incredible results started to arrive from the new James Webb Space Telescope, but rumours online and in the press started to spread that they were a death knell for the Big Bang theory. Of course, this was not the case, and served as a great example of the importance of media literacy, which is why I'm excited to have Ground News kindly sponsor this video. Ground News aggregates the world's news in one place, so you can compare coverage and verify your information, and it's been a big help in my research. For example, last month, solar storms were reported to disrupt communication and produce northern lights as far as the southern US. On Ground News, I was able to access over 200 articles published on this. At a glance, nearly 90% were from sources rated highly factual, indicating coverage is less subjective, which is important for science news. Comparing coverage is also interesting. NPR suggested the storms disrupted communications, while the majority of the sources, including phys.org, emphasized the northern lights and no serious problems. And so, if you're looking for a better way to get the full picture, I encourage you to visit ground.news/HOTU. Subscribe through my link to save 40% off unlimited access. And by subscribing, you're not only supporting the channel, but transparency in the media as well. It was 2013, and it was time to party. The attendees gathered in the main hall of the Paris Observatory, a grand building situated on the south side of Paris, near the old gates to the city. People got up to speak to congratulate each other on the successful mission and a job well done, including some remarks that there was, of course, more work to be done in the coming month. But before anyone could dwell too much on the tasks ahead, they marveled as cases were brought out from a back room. The cases were full of champagne, but not just any champagne. The organisers of the party had commissioned a special bottling, and the bottles had custom labels. On each bottle was printed an oval disc with an odd, speckled pattern. That pattern was the Cosmic Microwave Background, or CMB, a background radiation from just after the Big Bang that fills the entire universe. The European Space Agency's Planck satellite had collected the data to construct that image, the highest resolution all-sky image of the CMB ever made. The partygoers were celebrating the first public release of the Planck satellite's data, and they had every reason to celebrate. The data taken by Planck had confirmed the existing cosmological model and the story of the Big Bang. And on top of this, it had found evidence that the theory of inflation, a hypothetical event where the very early universe grew exponentially larger in a short amount of time, was on the right track. The Big Bang wasn't really a Big Bang. What we call the Big Bang, a name coined somewhat derisively by astronomer Fred Hoyle, is really just a generic description of the model of the universe where our cosmos used to be smaller in the past and will be larger in the future. In this model, there really isn't an explosive event that launches the creation of the universe, or a swift unfolding of space that gives rise to everything we know. Instead, it's much simpler. It is just a mere expansion from a smaller state to a bigger one. And from that theory, we can assign a number, 13.787, with an uncertainty of 0.02. A simple number, but this number is special. It's our current best estimate in billions of years of the age of the universe. Indeed, a direct consequence of the Big Bang theory is that there was a time before time. There was a moment when the universe simply became, and that moment existed 13.787 billion years ago. But that's only the dimension of time. As far as we know, the three dimensions of space that also make up our universe could be infinitely big. Yes, there is a limit to our observable cosmos, a boundary set by the finiteness of the speed of light. That limit sits about 45 billion light-years away. Beyond that, we presume that there is more universe, more stars and galaxies and gas and dust. But we don't know. It could be infinite. But not in the direction of time. Our universe could live infinitely into the future, even when our cosmos expands so far and so much that all the stars die out and existence is nothing more than a thin soup of particles near a temperature of absolute zero. The universe will still exist. Time will still march forward. Directions in space will still be in place. But the past is different. There is a limit to what we perceive, a boundary of our understanding. Even if the universe is infinitely big and will extend forever into the future, it all came from something. This simple, straightforward Big Bang model has been able to explain a wealth of observational data, like the apparent recession of galaxies away from us, the appearance of the cosmic microwave background, even the amount of light elements in the cosmos. In fact, no other cosmological theory is able to explain the existence of all those facts. But just like any other scientific theory or model, the Big Bang also has its shortcomings. And in 1979, physicist Alan Guth was poking at one of those shortcomings. In most theoretical models of the extremely early universe at the time, the cosmos seemed to naturally produce a significant number of defects, things like magnetic monopoles, cosmic strings, and other bizarre intergalactic warpings of space and time. However, none of these oddities had ever been observed in the real universe, and so Guth was trying to find a way to get rid of them. In a stroke of pure imagination, he wondered if the Big Bang really was a little more like its namesake than we'd previously suspected. A little bangier. And so he proposed a new entity to inhabit the cosmos, something called a scalar field. Scalar fields were not a new idea in physics. Quantum field theory, which alongside Einstein's general theory of relativity underlies our understanding of reality, is strange. Everything that exists, every particle and every form of radiation, is really the manifestation of an underlying quantum field that fills the universe. These quantum fields soak space and time the same way that olive oil and vinegar soak a piece of bread. Every particle has its own associated field, one for the photons, known as the electromagnetic field, one for the electrons, known as the Dirac field, and so on and so on. When one of these quantum fields has a local excitation, a region of higher energy vibrations, we see that as an independent particle. But of course, even when a patch of the universe contains no particles, the field is still there. Scalar fields are the simplest kinds of fields to exist. They just have a single value, a magnitude, associated with every point in spacetime. Every time you see a weather forecast with a map of temperatures across your local region, you are looking at a scalar field, a single number, in this case a temperature, associated with every point on the map. The eminent physicist Peter Higgs had already introduced the language of scalar fields decades before Guth, when he proposed what is now called the Higgs field, a scalar field working in the background of spacetime that is responsible for mass. But now it was Guth's turn to invent a new scalar field that radically altered the dynamics of spacetime in the distant past. This scalar field would permeate all of space and time, simply existing in the early universe. Then, randomly and suddenly, this scalar field would experience a dramatic phase transition, collapsing itself into a lower energy state. This collapse would provide the energy necessary to make the infant universe much, much bigger in a very short amount of time. Indeed, Guth estimated that if the universe inflated by at least a factor of 10 to the power of 50 or so in less than a second, then all of those troublesome defects would simply be scattered to the four corners of the cosmos, well outside our observable limits. And as well as this, the process of a rapid inflation event would solve two other challenges to the traditional Big Bang model. It would explain why the universe could have a uniform temperature despite its enormous size, because prior to inflation the cosmos homogenized, and why it appeared so flat. If you take any geometry you want and make it really, really big, then it will always appear flat to any local observers, just like the Earth appears flat in your garden. And so, because this idea of inflation so neatly explained several features of the observed universe, cosmologists began taking it seriously. And within a few years, Guth's original idea evolved. In the modern conception of inflation, first proposed independently by André Linde and the team of Andreas Albrecht and Paul Steinhardt, the quantum field didn't just suddenly jump to a new state, but instead slowly evolved into a lower energy state. It is this slow-roll inflation that allows the theory to put the bang in the Big Bang. At first, the inflation quantum field evolves into a lower energy state and powers the act of inflation. But at the end of this inflation, when the field is exhausted, the universe is large, cold, and empty. But this is where the magic of slow-roll inflation comes in, through a process called reheating. At the end of inflation, the quantum field doesn't just sit still in its lowest energy state. Just like a ball that's rolled down a hill, the field wobbles a little. This wobbling transfers even more energy back into the cosmos, not in the form of super rapid accelerated expansion, but in the creation of particles. In quantum theory, this is allowed. Quantum fields transform and intermingle all the time. So, in its dying breath, the quantum field responsible for inflation decays away, filling the universe with all the particles of everyday existence: the electrons, the photons, the neutrinos, and quarks. Even the dark matter. And so if there's anything that fits the popular conception of the Big Bang, inflation is it. Prior to this event, the universe was small, hot, and dense. When it was less than the tiniest fraction of a second old, however, inflation switched on. In another tiniest fraction of a second, the cosmos exploded in size, and at the end of that stupendous expansion, the universe relit itself, suffused with energy from the inflation field, spawning the particles that continue to inhabit the modern-day universe. But while this model can handily explain many cosmological mysteries, that's not quite enough for it to rank as a true scientific theory at the same level of prestige as, say, general relativity or the germ theory of disease. Most importantly, when it comes to inflation, we have more questions than answers. We do not know the identity of the quantum field that drove it, for even if it survives to the present day, it would be just as a broken shadow of its former self, sitting well beyond our ability to detect it. We also don't know why inflation lasted as long as it did, or why it had just the right evolution to power super rapid expansion, then decay away, flooding the cosmos with particles. Some cosmologists argue that due to these deficiencies, inflation is not a sound scientific theory. But the general concept of inflation, that a quantum field slowly evolved and triggered rapid expansion followed by a flood of particles, does make some generic predictions that are testable, and in fact, have been tested. The act of inflation didn't just rapidly expand the universe, it rapidly expanded all the tiny quantum foam that inhabits space-time. That quantum foam is submicroscopic, existing at the lowest level of reality. The incredible expansion of the cosmos under inflation turned that foam into still very small variations, but definitely bigger than they were. And this formed the seeds of structure. Tiny variations in space-time led to gravitational differences from place to place, and over time these differences grew, eventually becoming the grandest structures in the universe. Generic theories of inflation, regardless of the precise mechanics of the model, predict very particular statistical properties of structure in the universe that we observe. And the cleanest way to measure those structures is through mapping the cosmic microwave background, the leftover light from when the universe was only 380,000 years old. One major test of inflation involves something called the scalar spectral index. The map of the cosmic microwave background contains many variations, blotches of various sizes representing colder and hotter parts of the cosmos. Cosmologists can turn this map into a spectrum, measuring how many large fluctuations there are, how many medium, and how many small. A scalar index of 1 would tell us that every size of fluctuation adds the same contribution to the general pattern. Inflation models generally predict a scalar index slightly less than 1, and in 2013, the Planck missions measured this number to be 0.96 to an accuracy of 5 sigma. The Planck satellite measured the exact statistical properties predicted by inflation. Certainly, a champagne-worthy event. And so, even though inflation sits beyond the edge of known physics, involving properties and forces and fields that we do not yet comprehend, most cosmologists believe that something like inflation happened in the early universe. While there are other hypothetical alternatives to the inflation story, in the end they all tend to operate in much the same way. A rapid expansion of space, a flooding of particles, and the planting of the first seeds of structure. So even if inflation turns out to be an incorrect theory of nature, by all available evidence, the universe underwent something extraordinary in its earliest moments. Something that gave rise to the Big Bang. But if inflation is correct, if there was some exotic quantum field that drove a super rapid expansion of space and ignited the Big Bang, then the theory has some intriguing implications. Because before the Big Bang, there was inflation. And before inflation, there was a never-ending stream of inflation. In this view, powered by cutting-edge theoretical physics, what we think of as our universe is just one in an infinite chain of universes, each one bubbling and branching off of a stream that will continue forever. Inflation always was, and always will be. If this theory is correct, then what came before the Big Bang, before our universe, was the multiverse. In Fyodor Dostoevsky's 1846 novel, The Double, a Petersburg poem, a struggling young bureaucrat finds an unlikely companion, a man who looks exactly like him, except more cheerful. At first, the two men are friends, but then the double's charisma starts to take over the original's life. In the end, the original finds many copies of himself and is forced into an asylum. And though this is a fictional story, the concept behind it is not as far-fetched as it might seem, because somewhere in a galaxy far, far away, there could be a copy of you. Wearing the same clothes as you, the same age as you, the same life experiences, lovers, relatives as you, the same favorite restaurant and hated sports team. That copy of you, who also goes by the exact same name as you, could be watching a copy of this video. Right now, in parallel. The two of you watching it on exact duplicates of the screen at the same point in the video, hearing the exact same information, with the same voice. This copy would be inhabiting another universe, and this universe would be extremely distant from ours, far, far beyond the observable bounds of our cosmos. We could never access it, never travel there, and never exchange information with it, but it could exist, an exact replica down to the subatomic level. And that copy would not be alone. Somewhere even more distant than the nearest copy would be another one, and another, and another. In fact, there would be an infinity of yous, all watching this same video, in this precise moment. This is the reality of an infinite multiverse, a cosmos big enough to contain an infinity of universes, so large that it encompasses every possibility, every combination of molecule and atom and subatomic particle. And it copies each and every possibility an infinite number of times, both in the present and extending far into the future. The concept of a multiverse is staggering in its scope, but its tantalizing possibility is born in the fires before the Big Bang, in the event of inflation itself. One of the most vexing problems posed by inflation is just how it's supposed to stop. To create just the right conditions for our universe, the quantum field powering inflation must slowly evolve to its lowest energy state, and then finally come to rest. If the quantum field evolves too quickly, the universe expands too much, making a cosmos full of life impossible. And the end state, known as reheating, must also follow a particular path. Too much or too little energy injected back into the universe would render it desolate. To cosmologists, this seems very, very unlikely. Oddly, finely tuned, a strangely lucky coincidence. If the quantum fields behaved any differently, even very slightly, then our universe would have just kept on rapidly expanding, never slowing down, never coming to rest, and never becoming populated with particles and fields and stars and galaxies. And so this is where the concept of eternal inflation, comes in. In this model, once inflation starts up in the infant universe, it just keeps going. The entire universe, in the broadest possible sense, keeps exploding, doubling over itself in a never-ending cascade of accelerated expansion. Like a race car driver that never lets their foot off the pedal, the universe's expansion, once triggered in the first momentous act of inflation, never knows how to slow down. But this does mean that the universe has an ultimate beginning. Something had to kick off the first quantum field to start its journey towards inflation. So no matter what, the universe has a finite age in the past. But it can live forever into the future. There is always another part of the universe experiencing inflated growth, on and on and on, into infinity. Of course, we don't know if our universe, our inflation, our Big Bang was the first one, though it seems unlikely. And if not, what would have come before our inflation event was simply a previous one, and one before that, and so on, back into the mists of time. But our observable universe is obviously not experiencing this kind of runaway growth. There is dark energy, and our cosmos is accelerating in its expansion. But compared to inflation, this is quite leisurely, not the kind of breakneck pace powered by these early quantum fields. So how can we reconcile this observational fact with the concept of never-ending inflation? To make this work, physicist and inflation theory pioneer Paul Steinhardt proposed that our universe is just a tiny bubble, simply a piece of the much larger inflating spacetime. In our tiny bubble, a portion of the inflation-driving quantum field settled into a low-energy state, trapped there. That local condition caused our universe to separate itself, to pinch off from the wider cosmos. Here, inflation ended. Here, the portion of the quantum field behind inflation decayed away into the shower of particles and radiation that we see as the Big Bang. But not everywhere. Beyond the bounds of our universe, the rest of spacetime continues to inflate. And out there, in that wider spacetime, pieces of the quantum field continue to pinch off, separate, and settle down. Each time a portion pinches off, a new universe is born, with a new set of particles and radiation, a new realization of the cosmos. But of course, this proposed multiverse wouldn't be infinitely big. However, it would quickly approach scales that might as well be. In just a single event of inflation, our universe already became 10 to the power of 50 times larger than its observable volume. And that was from a period of inflation lasting less than 10 to the power of minus 30 seconds. Imagine inflation lasting for an entire second, or a minute, or 10 billion years, or who knows how long since the initial spark. This is the inflationary multiverse, a giant, ever-growing collection of individual universes. Each universe is separated from the next by an almost uncountable number of light years, and that distance is growing. Because inflation causes space to expand faster than light, each bubble universe is flying away from every other bubble universe faster than light. There can be no connections among them, no communication, no influence. And surprisingly, it is possible, at least in principle, to test this idea. Even though the other universes of the multiverse are unreachably far away from us now, they might not always have been. If another universe just happened to spawn near ours, then we might have briefly collided before going our separate ways. That collision would appear to us as a circle in the sky, a ring created at the intersection of our two bubbles. Many researchers have searched for these circles, both in maps of galaxies across the modern-day universe and within the cosmic microwave background. However, while there have been some intriguing hints of a signal, to date nothing has withstood further scrutiny. This lack of a detection does not rule out the multiverse idea, because there was only a slim chance anyway that our young universe would have intersected with another. But unfortunately, beyond that idea, there aren't really any rigorous ways to detect the existence of the multiverse, since by definition, the rest of the inflating universe exists beyond our observable horizon, impossible to reach. And it is because of this that many theoretical physicists have decried the idea of the multiverse, arguing that it's not a valid scientific theory. Indeed, among these are Paul Steinhardt himself. Even though he was one of the originators of the eternal inflation idea, he's later turned to become a vocal critic of all inflation theories. After all, the multiverse fails to explain anything about our own particular universe. Within the multiverse, every possibility, every arrangement, and every combination of particles and forces is possible. That means there's nothing special about this particular arrangement that we find ourselves in. But there's also nothing special about any other arrangement. You simply can't tell from observations of your own universe whether the multiverse exists or not, which unfortunately isn't a very good way to build scientific theories. On top of this, it's also currently impossible to tell the potential variety of universes contained in the multiverse, as the details would depend on the exact physical mechanism that drove inflation in the first place and when exactly inflation occurred. In the simplest scenario, the bubbles of the multiverse are just more universe. The same forces, fields, and particles that we're used to here, just in a variety of combinations. If we could visit another bubble universe, for example, we would see the familiar photons and gluons and quarks and so on, and those particles would interact via the same forces that we have here. So there would still be stars and galaxies and a cosmic web, just in a different pattern. But depending on what powers inflation, it's also possible that those universes could have different combinations of particles and forces, or even different fundamental constants. Different bubble universes could have different speeds of light, or different electron masses, or no electrons at all. Much of the physics that we take for granted could be totally different. Of course, most of those bubble universes would be completely inhospitable to life or the formation of stars, or even macroscopic structures in general. But with so many universes, everything gets a chance. This is one of the strange features of such a large multiverse, and also with infinite multiverses. There isn't just one occurrence of every single possibility. There are a huge number of occurrences of every single possibility. This means that there would be countless bubble universes where dark energy just rips everything apart before anything can form. There would be countless universes where light travels too slowly. There would be countless universes where electrons are the size of footballs. And there would be countless universes where everything is just fine, with the same kind of physics as we have in our universe. And the possibility of copies of you comes from the idea that there might only be a finite number of ways to combine all the matter in the universe. This idea is hypothetical, relying on our current understanding of quantum information. If it's true, and there really are only a limited number of ways that electrons, quarks, neutrinos, photons, and dark matter can position themselves in any universe, then with a large enough amount of bubble universes within the multiverse, each and every combination of particles wouldn't just appear once, but many, many, many times. But this remarkable extrapolation doesn't answer the key question. How could we ever know? If it's practically impossible to test, what other options do we have? There is one possibility. Physicists, including André Linde, one of the originators of eternal inflation, think we could gain hints of this multiverse through theory. If we can find a mechanism behind inflation and are able to test that, then we would know for sure that inflation happened because of an out-of-control quantum field. And if we can prove that eternal inflation is a generic feature of that particular inflation model, then we can be confident that a multiverse exists. But what theory could explain such an extreme event? Well, without realizing it, as it turned out, the early pioneers of eternal inflation were developing the physical grounding needed to explain one of the most challenging aspects of string theory, the infamous leading candidate for a theory of everything, the troublesome fact that string theory can't tell us what kind of universe we live in. Legend has it that in the ancient land of Phrygia, in what is today central Turkey, there was a knot tied to an ox cart. It was no simple knot. The legend had grown that anyone who could untie this knot, which was so complex, so intertwined, and so complicated that nobody could figure out where it began or ended, would eventually rise to become king of all Asia. And so, hearing of this legend, the Macedonian ruler and general Alexander the Great had sought it out. He was in the midst of his conquest of the Persian Empire and very much wanted what the knot promised. There the knot stood, strong, tied, fixed, implacable. As his followers looked on, Alexander had devised a clever, simple, swift solution. He took out his sword and cut the knot in two. Modern theoretical physicists may not share many similarities with Alexander the Great, but they did discover a Gordian knot of their own, and came up with an equally swift and brutal solution. String theory is an audacious attempt to do two things at once. On the one hand, it promises to provide a quantum theory of gravity, which has remained an unsolved riddle in physics ever since the development of the seemingly irreconcilable general relativity and quantum mechanics over a century ago. Try as they might, physicists have routinely failed to definitively bring gravity into the quantum realm, though string theory is still the most popular attempt. Simultaneously, string theory also hopes to be a theory of everything. Literally, a single theory grounded in a simple set of equations that describes our entire reality, explaining what the forces of nature are and why they have the properties that they do, along with explaining all the particles of nature and why they have the properties they do. Ultimately, if string theory lives up to its promise, if you have any question about fundamental physics, it will have the answer. String theory hypothesizes that what we think of as particles are anything but. The fundamental units of reality are vibrating loops. Different vibrations of the loops correspond to different particles, like different vibrations on a plucked guitar string correspond to different notes. But 3 dimensions just isn't enough for these tiny strings to vibrate in all the ways needed to explain the vast array of particles that we observe in nature. So string theory also posits the existence of extra spatial dimensions, either 10 or 11 depending on the theory. But all these extra dimensions are invisible to us, curled up on themselves at the smallest of scales, well below the threshold of anything we could ever hope of detecting. And even though we have no evidence for the existence of these extra dimensions, they are necessary for string theory to work. For it is within these extra dimensions that the strings have the freedom they need to vibrate in all the ways they need to. But there is one not insignificant problem with this curled-up extra dimensions idea. And that is that all the extra dimensions of the universe can curl up on themselves in a tremendously huge number of ways. There are somewhere around 10 to the power of 500 different options. Each one of these options places a different set of restrictions on the vibrations of the string, just like different guitar neck lengths change what kind of notes the instrument can make. Because the vibrations of the strings are responsible for the physics that we see in the universe, and the shapes of all these extra dimensions govern how the strings can vibrate, each potential way of curling up the extra dimensions gives rise to a completely different universe, with different particles, different forces, and different fundamental constants. And we just don't know which universe we live in. We don't have the sophistication yet to understand the tangled mathematics of string theory, We know that the shapes of the extra dimensions determine vibrations, and that vibrations give rise to particles, but we don't know how all of that works. If you hand a string theorist a particular configuration of the extra dimensions, they couldn't tell you what kind of physics arises from it. String theorist Leonard Susskind called this the landscape. It's the set of all possible configurations of the extra dimensions, each one leading to a completely different set of laws of physics for a universe. This landscape is imaginary. It's a mathematical mapping of all the possibilities, and our universe occupies one single point in this landscape, just one speck amongst all the 10 to the power of 500 possibilities. To visualize this landscape, imagine walking barefoot through a vast field filled with rolling hills, sporadic rocky outcrops, wooded glades, peaceful streams, and placid lakes. As you traverse the field, every step you take samples a different portion of it. Perhaps one footstep lands on a soft cushion of lush grass, perhaps another slips against a moss-covered stone, and yet another plunges into frigid waters. But the landscape laid before you isn't just a universe, it's a universe of possibilities, a mathematical construct that contains all the variations of a cosmos that could possibly exist within string theory. Each step represents the realization of one universe, one cosmos, one arrangement of matter and forces and radiation and constants. The lush hill to your right, that's a region where the cosmological constant has a small enough value for life to survive. The bare patch on the other side of the hill, gravity is too strong there. The swift current of the river is all the universes where the speed of light is too fast, or the electric charge too low. Our universe exists as a single point in this landscape, one particular sample from the grand tapestry, where the nature of the cosmos permits life to exist, where the configurations of the extra dimensions allow just the right vibrations of strings to make stars, galaxies, and us. But even if we did know how to connect configurations of extra dimensions to vibrations of strings, we still wouldn't have a way to explain why our universe manifested in this particular way. Why did our universe choose this arrangement of dimensions instead of any of the others? This arrangement seems favorable to the development of intelligent life, at least as far as we understand it, but most of the others are presumably void. Too big, too cold, too small, too weird. So, as string theorists began to develop the concept of the landscape, they kept running into this nasty Gordian knot. Why were these extra dimensions of our universe tied up in this particular way instead of any other? Was it just an accident? Or was there something more? And this is where eternal inflation could save the day. The landscape was a deeply hypothetical idea, a plane of possibilities mapping out every allowable universe. But it wasn't a thing. It wasn't a place that birthed new universes or a wider meta-universe. But eternal inflation and its implied multiverse, though also highly theoretical, they were concrete, physical. And so in the 1990s, string theorists like Leonard Susskind and cosmologists like André Linde and Sir Martin Rees got together. They realized that they were coming at the same problem from opposite directions. The cosmologists were trying to understand the properties of our universe and hit upon the concept of a multiverse, that ours was just one of many. The string theorists were grappling with the possibility of an astounding number of possible universes, of which ours was just a single realization. Perhaps this was no mere coincidence. Perhaps there was something deeper going on. The string theorists could imagine the landscape but didn't know how to create a universe from it. And yet here was the multiverse, a way that inflation naturally, effortlessly constructed every possible kind of cosmos. The multiverse idea, through eternal inflation, gives a physical mechanism to the string landscape. In other words, the multiverse could be how the string landscape manifests itself. Each new bubble universe can have its own set of physical laws, its own population of particles and energies and forces. Each one of those bubble universes corresponds to a singular point on the landscape, and each one of those universes is a sample of the possible configurations of the extra dimensions, a single chord on the instrument of the cosmos that vibrates its own unique set of frequencies. But, as alluring as this concept is, as of right now the connections between string theory and eternal inflation are tenuous at best. We do not fully understand the physics of inflation, assuming that inflation even is a correct description of the extremely early universe. That means that we don't know how deep the multiverse goes, whether the bubble universes only sample different arrangements of the familiar forces or particles, or manifest new configurations of the extra dimensions that lead to brand new physics. But the connection is attractive. That not only is our universe one of many, but over the span of creation every possible manifold arises, every kind of possibility. This also saves string theory from the seemingly impossible task of having to explain why our universe has the properties it has, why it has this particular curling of extra dimensions instead of any other. With every possibility realized, with every kind of cosmos manufactured, we are guaranteed to find ourselves only in a universe that has the physics to make us possible. We are here, at this point in the string landscape, because we could not exist anywhere else. Those universes are out there, sampling every portion of the landscape countless times, but they are almost all empty and devoid of life. We are here in this one because it is the only universe that we can call home. This line of thinking is known as the anthropic argument, that the universe is the way it is because otherwise we wouldn't be here to observe it. And so while it is the ultimate conclusion of the string landscape and multiverse ideas combined, many scientists argue that this line of thinking has led nowhere useful. We can't ever directly test the string landscape because according to the string landscape, we were always going to arise anyway. We can't say why our universe has this configuration beyond that it is compatible with life. In response, some theorists have attempted to put the landscape on firmer grounds. For example, using some simplified calculations born from string theory, they hope to be able to say that the amount of dark matter or dark energy, or the mass of the electron, or any of the other parameters that makes physics work the way we know it to work, are the most probable outcomes in the landscape. That kind of analysis won't erase worries over the anthropic argument, but it would at least ease some of the concern that our specific universe is so special and finely tuned. But of course, again, this is all highly speculative. We don't know how, or even if, the string landscape connects to eternal inflation. But if it does, it offers a startlingly different view of our universe and the Big Bang. Before the Big Bang, there would be inflation. Before inflation, there would be eternal inflation and the multiverse. And before it all would be the string landscape. But not in the sense that the landscape is a physical entity. The idea is that before there was even the possibility of the cosmos, there was the reality of string theory and the landscape. With these rules in place, the universe could simply proceed, evolving according to the machinations of strings and higher dimensions, that manifested in the event of the first inflation, which began the race towards multiplicity. And from there, the separate bubble universes expanded and explored, discovering every nook and cranny of all possible string dimensions. But this extension of thought, whether grounded in string theory and the multiverse, or some other theory of physics that we've yet to dream of, leads us back to the ultimate question. Why is there something rather than nothing? What created the string theory landscape? What came before the Big Bang? If the laws of physics made the universe, our cosmos, the multiverse, the landscape possible, then why are there laws of physics in the first place? There was a time before your birth. And before you were born, before your mind organized itself into conscious awareness, before there was you, the universe still existed. The evidence is all around you. Your parents, the memories and stories of older generations, photographs and mementos and monuments from before their time. Your birth may have been the beginning of you, but it was not the beginning of the world. And so is this the case with our universe too, or our multiverse? We have seen that our cosmos may have ignited in a quantum fire known as inflation. That inflation event may not have been alone. It may be part of a never-ending string of eternal inflation, creating a grand cosmos that will continue inflating forever, and in the process unfolding a multiverse of possible bubble universes. And that multiverse potentially solves the riddle of the string landscape, in the process explaining why our universe has the properties it does to be amenable to life and intelligence. But, though motivated by decades of research into theoretical physics, string theory still remains speculation. There is no experiment that has validated the theory, and indeed, because we lack the mathematical sophistication to tie together configurations of the extra dimensions with the vibrations of the strings, we actually can't test string theory. As powerful as its mathematics may be, it has not yet risen to the challenges that a proper physical theory must overcome. It cannot make predictions that can be tested against experiment. Even eternal inflation, while still on shaky ground, is at least motivated by a physical theory grounded in our current understanding of physics, the language of quantum fields, and most cosmologists strongly suspect something like inflation happened in the early universe. That said, there are other alternatives. The story of inflation, eternal inflation, and the string landscape is not the only approach to peering into the grey mists behind our Big Bang. In 2001, 4 physicists, Justin Curry, Bert Overath, Paul Steinhardt, and Neil Turok, proposed a completely different cosmological model, one that was still anchored in the latest thinking on string theory, but without the need for inflation at all. In this model, before our universe, before what we would call the Big Bang, the cosmos was composed of giant, floating brains. These brains are not biological networks, but the name given to cosmic strings that stretch over more than one dimension. In this model, our 3-dimensional universe is one such gigantic brain, and it floats in an endless void of higher dimensional reality. Unfortunately, we cannot access these higher dimensions because the particles that make up our reality are restricted to live on this brain, and so our universe only appears 3-dimensional. Long ago, this theory posits, before our Big Bang, the brain of our universe was cold, empty, and featureless. But it was not alone. There were other brains existing in the higher dimensional reality as well, and at some time, another brain collided with our own. The brains met at a point, releasing a storm of energy and triggering shockwaves that rippled through them. From our perspective, embedded inside the brain, this looks like a Big Bang, a hot flash of energy at a singular point that floods the cosmos with particles and radiation. Known as ekpyrotic cosmology, from the Greek word for fire, the model is able to reproduce the broad properties of our cosmos: the flatness, the lack of defects, the appearance of a Big Bang, expansion, and even the formation of structures, without invoking inflation and without building a multiverse. This ekpyrotic model also has one additional feature: the ability to reignite the cosmos. Our brain could collide again with another one in that higher dimensional space. That would start the process over again, igniting a fresh Big Bang. What we see as a singular event in our past is then just as regular and repeatable as a ball bouncing on the floor. And the ekpyrotic model isn't the only one that claims we live in a never-ending cycle of Big Bangs. Another approach to solving the riddle of marrying gravity with quantum mechanics, known as loop quantum gravity, suggests that what we see as a smooth and unbroken fabric of space-time is really a series of discrete elements, like the pixels of your computer screen. In our classical understanding of cosmology, rooted in general relativity, the universe begins as a singularity, a point of infinite density. But in loop quantum gravity, there's no such thing as the Big Bang. It is impossible to bring matter or space or time into a region smaller than the fundamental pixels of reality. When one attempts to do so, a pressure emerges that resists the collapse, the same way a spring gets hard to push the smaller you make it. So when the universe collapses in on itself, it reaches a point where natural quantum reactions fling it back outwards, subverting the appearance of a singularity and igniting a new Big Bang in the process. And there are still more models and ideas that allow for the creation of new universes, like Roger Penrose's conformal cyclic cosmology. In this model, in the extremely distant future, the universe is so thin, so cold, and so spread out that space and time are rendered meaningless, opening up the possibility of a new Big Bang springing to life. And so, whatever the case may be, the answer to the origins of our Big Bang, whether through inflation, string theory, loop quantum gravity, or something even more exotic, lies somewhere in the land of quantum gravity. We have to understand how gravity operates at extreme scales to push deep enough into our own past that we can understand the origins of our universe. We know that the singularity of general relativity, the infinitely tiny point at the beginning of our cosmos, is wrong. It is simply a sign that our mathematics is breaking down, and we need a new understanding. And that new understanding may even require rewriting the definition of time itself. Our conception of the universe includes not just particles and radiation, not just forces and interactions, but the very fabric of space-time itself. Of course, we can envision a beginning to space, an imaginary spark that allows space to manifest and unfold itself, becoming the universe as we see it. But the beginning of time? How can there be cause and effect before the existence of time? How can the clock of our universe start before there was a clock? The beginning of the universe includes every feature of it, including time itself. So we can push the beginning of our universe beyond the edge of the Big Bang, into the realm of eternal inflation and the string landscape. But even in these most advanced and hypothetical ideas, there is still a start, still a beginning, still a time at which time begins. If this sounds like a paradox, it's because it is. There is much about time that we currently do not understand and may never understand. So what can we do? Our conceptions of time in physics are already muddled and contradictory. In quantum mechanics, time is treated as an external parameter, a fact of the universe that uniformly marches forward, allowing observers to make observations and for interactions to take place. Whereas in general relativity, time is fluid, relative, and tied into space through a harmonious fabric. To understand the universe, we must reconcile these perspectives. Very simply, we cannot speak confidently about a moment before time until we can understand with confidence what time exactly is. And so for now, our thoughts on space and time aren't sophisticated enough to grapple with the beginning of it all, because terms like beginning are so rooted in our biological existence, so grounded in our fundamental conscious perspectives on the world around us, that we may not be able to escape our biases, even when we extend them to the farthest reaches of our most advanced theories. Indeed, the very process of time, the segregation of the past, present and future, may break down in the early universe. Conditions may become so extreme that the separation between before and after may lose all meaning. Causality may become a jumbled mess. In the earliest moments of the cosmos, moments may be meaningless. This means it may ultimately be fruitless to search for an ultimate beginning, a before the Big Bang, because time itself, at least the way we currently grasp it, would become a useless framework for organizing the universe. And yet, even if we could surmount all these difficulties, that would still not be the end. Because no matter what, no matter which theory we propose to explain our own origins, whether an infinite chain of multiverses or colliding brains or an endless cycle of repeated Big Bangs, there is still something, rather than nothing. There is still physics, there are still rules, laws, and ordered harmony that allow for the existence of the cosmos. If it's inflation, then there's a quantum field. If it's colliding brains or a landscape, then it's strings. If it's loop quantum gravity, then it's discrete units of spacetime. And our voyages into the horizons beyond the beginning of the Big Bang will undoubtedly reveal even more rules, more structures, more laws that allow for the creation of laws. And so whatever we find there, a fundamental reason that reality exists and is, may just be forever beyond us. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.